Hello everyone, welcome to the new section of the course, Barrier, Future and Pipeline Design Patterns. In this section we'll see the three patterns, Barrier Concurrency, Future Design and Pipeline Design, and work with them. Now we move on to the first video of this section that deals with Barrier Concurrency Pattern. In this video we're going to take a look at the concept of barrier pattern. Then we'll create a barrier pattern and implement it. Let's start. The purpose of barrier pattern is simple. Put up a barrier so nobody passes until we have all the results we need. Something quite common in concurrent applications. Let's look at its description. Imagine the situation where we have a microservices application where one service needs to compose its response by merging the responses of other three microservices. This is where the barrier pattern can help us. Our barrier pattern could be a service that will block its response until it's been composed with the results returned by one or more different Go routines or services. And what kind of primitive do we have that has a blocking nature? Well, we can use lock, but it's more idiomatic in Go to use an unbuffered channel. What are our objectives? As its name implies, the barrier pattern tries to stop an execution so it doesn't finish before it's ready to finish. The barrier pattern's objectives are to compose the value of a type with the data coming from one or more Go routines, control the correctness of any of those incoming data pipes so that no inconsistent data is returned. We don't want a partially filled result because one of the pipes has returned an error. For our example, we're going to write a very typical situation in a microservices application, an app that performs two HTTP GET calls and joins them in a single response that will be printed on the console. Our small app must perform each request in a different Go routine and print the results on the console if both responses are correct. If any of them returns an error, then we print just the error. The design must be concurrent, allowing us to take advantage of our multi-core CPUs to make the calls in parallel. In the diagram, the solid three lines represent calls, and the dashed lines represent channels. The balloons are Go routines. So we have two Go routines launched by the main function, which could also be considered a Go routine. These two functions will communicate back to the main function by using a common channel that they've received when they were created on the make request calls. Let's look at the acceptance criteria. Our main objective in this app is to get a merged response of two different calls, so we can describe our acceptance criteria like this. Print on the console the merged results of the two calls to the links shown here. These are a couple of public endpoints that respond with data from the incoming connections. They're very popular for testing purposes. You'll need an internet connection to do this exercise. If any of the calls fails, it must not print any result, just the error message or error messages if both calls failed. The output must be printed as a composed result when both calls have finished. It means that we cannot print the result of one call and then the other. Now we'll look at unit test integration. To write unit or integration tests for concurrent designs can sometimes be tricky, but this won't stop us from writing our awesome unit tests. We'll have a single barrier method that accepts a set of endpoints defined as a string type. The barrier will make a GET request to each endpoint and compose the results before printing it out. In this case, we'll write three integration tests to simplify our code so we don't need to generate mock responses. First, we'll create a new document called barrier.go and another file, barriertest.go. Now open the barrier test file and add the lines as shown. We have a single test that will execute three subtests. The first test makes two calls to the correct endpoints. The second test will have an incorrect endpoint, so it must return an error. The last test will return the maximum timeout so that we can force a timeout error. We'll have a function called barrier that will accept an undetermined number of endpoints in the form of strings. Its signature could be like this. As you can see, the barrier function doesn't return any value because its result will be printed on the console. Previously, we've written an implementation of an I/O writer interface to emulate the writing on the operating system's stdout library. Just to change things a bit, we'll capture the stdout library instead of emulating one. The process to capture the stdout library isn't difficult once you understand concurrency primitives in Go. So let's add the function. Don't feel daunted by this code, it's really simple. First, we created a pipe. A pipe allows us to connect an I/O writer interface to an I/O reader interface so that the reader input is the writer output. We define the os.stdout as the writer. Then to capture stdout output, we'll need a different Go routine that listens while we write to the console. As you know, if we write, we don't capture, and if we capture, we're not writing. The key word here is while. It's a good rule of thumb that if you find this word in some definition, you'll probably need a concurrent structure. So, we use the Go keyword to launch a different Go routine that copies the reader input to a bytes buffer before sending the contents of the buffer through a channel that we should have previously created. At this point, we have a listening Go routine, but we haven't printed anything yet. So we call our not yet written function barrier with the provided endpoints. Next, we have to close the writer to signal the Go routine that no more input is going to come to it. Our channel called out blocks execution until some value is received, the one sent by our launched Go routine. The last step is to return the contents captured from the console. OK, so we have a function called capture barrier output that will capture the outputs in stdout and return them as a string. We can write our tests now. Let's add the tests. All the tests are very easy to implement. All in all, it's the capture barrier output function that calls the barrier function. So we pass the endpoints and check the returned result. Our composed results directed to http://http://bin.org must contain the text accept-encoding and user-agent in the responses of each endpoint. If we don't find those texts, the test will fail. For further debugging purposes, we log the response in case we want to check it with the -v flag on the Go test. We'll edit our code further. This time we use an incorrect endpoint URL, so the response must return the error prefixed with the word error that we'll write ourselves in the barrier function. The last function will reduce the timeout of the HTTP GET client to a minimum of 1 millisecond, so we force a timeout. Let's add to our test further. The timeout milliseconds variable will be a package variable that we'll have to define later during implementation. Now we'll look at the implementation. We needed to define a package variable called timeout milliseconds. Let's start from there. Open the barrier.go file and add the code lines as you can see here. The initial timeout delay is 5 seconds. 5,000 milliseconds, and we'll need these packages in our code. OK, so we need a function that launches a Go routine for each endpoint URL. Do you remember how we achieve the communication between Go routines? Exactly, channels. So we'll need a channel to handle responses and a channel to handle errors. But we can simplify it a bit more. We'll receive 2 correct responses, 2 errors, or a response and an error. In any case, there are always 2 responses, so we can join errors and responses in a merge type. Add these lines. So, each Go routine will send back a value of the barrier resp type. This value will have a value for ERR or a value for the resp field. The procedure is simple. We create a channel of size 2, the one that will receive the responses of the barrier resp type. We launch both requests and wait for 2 responses, and then check to see if there's any error. Following the previous description, we created a buffered channel called in, making it the size of the incoming endpoints, and we deferred channel closing. Then, we launched a function called makeRequest with each endpoint and the response channel. Now we'll loop twice, one for each endpoint. In the loop, we block the execution waiting for data from the in channel. If we find an error, we print it prefixed with the word error, as we expect in our tests, and set hasErrorVar to true. After 2 responses, if we don't find any error, that is, hasError equals to false, we print every response and the channel will be closed. We still lack the makeRequest function. Let's add that. MakeRequest function is a very straightforward function that accepts a channel to output barrier resp values to and a URL to request. We create an http.client and set its timeout field to the value of the timeout milliseconds package variable. This is how we can change the timeout delay before the in function tests. Then we simply make the get call, take the response, pass it to a byte slice, and send it through the out channel. We do all this by filling a variable called res of the barrier resp type. If we find an error while performing a GET request or passing the body of the result, we fill the res.err field, send it to the out channel, which has the opposite side connected to the original Go routine, and exit the function, so we don't send 2 values through the out channel by mistake. Time to run the tests. Remember that you need an internet connection, or the first 2 tests will fail. We'll first try the test that has 2 endpoints that are correct. Save this file, open the terminal, and run this command. Perfect. We have a JSON response with a key, headers, and another JSON response with a key user agent. In our integration tests, we were looking for the strings user-agent and accept-encoding, which are present, so the test has passed successfully. Now we'll run the test that has an incorrect endpoint. For that, we'll run another command. we can see that we have had an error where http://malformed-URL has returned a no such host error. A request to this URL must return a text with the keyword error prefixed, as we stated during the acceptance criteria. That's why this test is correct. The last test reduced the timeout to 1 millisecond. We'll again run the command. Again, the test passed successfully and we've got 2 timeout errors. The URLs were correct, but we didn't have a response in less than 1 millisecond, so the client returned a timeout error. The barrier pattern opens a door of microservices programming with its composable nature. It could be considered a structural pattern, as you can imagine. The barrier pattern is not only useful to make network requests, we could also use it to split some tasks into multiple Go routines. For example, an expensive operation could be split into a few smaller operations, distributed in different Go routines to maximize parallelism and achieve better performance. In this video, we understood the barrier pattern successfully.